Chapter 17, Part 2, we are going to continue our work with Bernoulli trials, but switching gears a little bit, we are now going to look at binomial models. So binomial models are another type of Bernoulli trial, so they still need to have the same requirements. They must have two outcomes, a fixed probability of success, and independent trials. Now, so far we've looked at geometric models, and geometric models focus on the number of trials until the first success occurs. The main thing we were looking at was that first success. Okay, binomial models are a little bit different. Binomial models focus on the number of successes in a given number of trials. So if you think back to the very first Bernoulli trial we saw, Jerry-O was shooting the soccer ball out on the soccer field trying to hit that crossbar. We were looking at first how long it would take until he hit the crossbar. That was a geometric model. In a binomial model, we would say, hey Jerry-O, I'm going to give you 10 tries. You get 10 trials. We're going to count how many times you reach that success. A big difference is that in order to use a binomial model, we have to have a specific number of trials. So first up, we'll look at some notation again. Okay, many of these are going to be the same as we saw for geometric. So let's start with the ones that we know are the same. P is still representing the probability of success. Q is the probability of failure. Okay, N in this case is a new variable. N is going to represent the number of trials. So that's how many attempts they get. And X is now going to represent the number of successes in the given trials. So I might give you 10 trials. You might be looking for the chance that you make 5 of them. I might give you 20 trials. You might be looking for the chance that you make 2. Now, I put the technical equations here for finding the probabilities. We won't really ever use these, so we don't need them. We're going to do all of this again right on our calculator, which the AP exam is totally fine with. Okay, they might again ask you to find the expected value. To find that expected value, you're going to take P, the probability of success, and multiply it by the number of trials. To find standard deviation, I'm going to square root probability of success times the probability of failure times the number of trials. Okay, again, these formulas will be given to you, so you do not need to memorize them. They'll be given to you on the exam. Okay, very similar to last lesson, we can use our calculator. Now that we're looking at binomial distributions, we want to make sure we're picking either the binomial PDF or binomial CDF. PDF, again, is used for x equals probabilities, and CDF is for any sort of inequality. So we're going to see less thans and we're going to see greater thans today. So let's go ahead and look at an example. Okay, example 1 says, Anna loves to shop. One of her favorite stores is running a special where customers get a keychain in their bag after each purchase. They claim that 20% of the purchases will have a dog keychain, 40% will have an otter keychain, and the remaining purchases will have a giraffe keychain. Anna really only cares about getting the dog keychain. So again, they didn't ask me to write down conditions, but I am going to. I don't really have a whole lot of room, so I'm just going to do it down here at the bottom. In order for this to be binomial, we would need there to be 2 outcomes. Now, technically, there's more than 2 keychains that are being offered, but it says that Anna really only cares about getting the dog keychain. So to me, I'm going to say that there are two outcomes. In Anna's mind, she's either getting the dog or she doesn't get the dog. That's all she cares about. Okay, after two outcomes, I'm going to look for independence. Do we think that each of these keychains are being randomly put into the bags? I can't tell for sure, but I'm going to assume that independence is true. Hopefully the keychains are randomly placed into the bags. And the last one, I need to make sure there was a fixed probability. The one I'm looking for is the dog keychain, which is 20%. That should stay the same each time. So part A says, suppose Anna makes 5 purchases. She's a big shopper. She's making 5 purchases at the store. We want to find the probability that she gets exactly 2 dog keychains. So exactly 2 means I'm looking for where x is equal to 2. Now the difference with binomial is that I should also be able to find an n value, how many trials there were. Anna's making these 5 purchases, which is 5 attempts at getting the keychain, so this means that n is equal to 5. Because my x wasn't equal to, I'm going to use my binomial, spelling is hard, PDF in your calculator. We're going to find this in the same spot, so second bars, binomial PDF is up a little bit here. It's asking you for one extra thing this time. So trials is first. Those are the 5 purchases that Anna's making. P is still the probability of her getting that success, so that's my 0.2, the 20%. And the x value I'm looking for is 2. Okay, make sure you write each of these down and label them. So I have my n, p, and x, and we get 0.2048. So about a 20% chance here that Anna will get exactly 2 dog keychains when she makes 5 purchases. Okay, suppose Anna makes 10 purchases. Holy cow, girl, you do have a shopping problem. So n is 10 now. She's making 10 different purchases. We want to find the probability of getting up to 5, typo here, dog keychains. So she wants up to 5. So she likes the dog keychain, but she doesn't want more than 5 of them. So up to 5 means that x would be less than or equal to 5. Okay, again, because it's a inequality, I'm going to use my binomial CDF this time. The CDF will do that adding for me. It'll find the chances she gets 1 dog, 2 dogs, 3 dogs, 4 dogs, and 5 dogs, and add them together. So I'm going to binomial CDF. My trials this time is 10. Probability of success is 0.2. X value is 5. Okay, the reason that this is so high is because we are looking at quite a lot of different outcomes. We were looking at 1 dog, 2 dogs, 3 dogs, 4 dogs, or 5 dogs. All of those dog keychains were accounted for, so it makes sense that this probability would be a little bit higher. Let's go ahead and turn our page and look at another example. All right, example 2. Colin loves to run, and I've heard he can run a mile under 5 minutes, which is just absolutely insane to me. Did you know that only about 10% of people can run a mile under 5 minutes? I mean, I would believe it because my mile time is much higher than 5. We will consider people who have a mile time of under 5 minutes, quote, fast runners. So, Colin, you're a fast runner. If we select 5 people at random, we want to find the probability of each outcome described below. So each time here we're selecting 5 people, which is going to be my n value. Okay, in part A, I want to check conditions. I want to see if this meets the conditions to be a Bernoulli trial. So I'm looking for 2 outcomes. Now I know that people could run a lot of different mile times here, but we're really looking for whether people are fast runners or not fast runners. So I'm going to say that there are 2 outcomes. You're either a fast runner like Colin, or you're a slow runner like Soto. A second condition, I need independence. We're just randomly selecting 5 people, so I don't think that there's going to be any issue here with independence. Those 5 random people should have no impact on whether they're fast runners or not. So definitely independent. And the third condition, do we have a fixed probability of success? Not sure where this data came from, but it says that 10% of people are those fast runners, so we're going to assume that that stays the same. Okay, part B says find the chance that there are exactly 3 fast runners in the group. So I'm looking for the chance that x is equal to 3. Now, equals to 3 means that I would be using a PDF. This is binomial. So my trials are 5. I'm selecting 5 people at random. The chance of them being a fast runner is 10%, so 0.1. And the x value I'm looking for is 3. So I have 5.1 and 3. Which gives us a 0.0081. Very, very small chance that 3 out of my 5 are fast runners. Part C says find the chance there are no more than 3 fast runners in the group. So that means that x must be less than or equal to 3. I don't want more than 3 fast runners. So I'm now using a inequality, so I'm going to have a binomial CDF, CDF standing for cumulative. I'm still working with 5 people, so that's my n. My probability of success is still 0.1, and my x value is still 3. So the only difference here is that I'm using a PDF and CDF. So definitely make sure you take your time when you're thinking about those. 5.1 and 3 gives me 0.9995. Right, now a lot of times students ask me, why are they so different? The only difference was PDF versus CDF. With the PDF, we found the chances that exactly it was 3. It was extremely specific. We were looking for 3 runners exactly, no more, no less. In part C, we're looking for something that's much more broad. We're looking for no more than 3 runners. So it could be 0 fast runners. It could be 1, it could be 2, it could be 3. There's way more scenarios here, so it makes sense that that probability would be larger. Okay, now part D is a little bit different. We are now looking for at least 3 fast runners. So that means I need 3 or more. So my x is now greater than or equal to 3. Now, greater than or equal to problems always involve a little bit more work because my CDF can only calculate lower. Cumulative is always going to start at that number you gave them and count below. So what I'm going to do is real quick just write out my sample space. I could have 0 fast runners, 1 fast runner, 2, 3, 4, or 5. What I'm doing is looking for greater than or equal to 3, so this is my goal to find. Okay, my calculator, though, can only find things to the left. So I'm going to use my calculator to find this area right here. If I knew what this percentage was, I could take that percentage, subtract it from 1, because again, this whole thing should add to 1, and it would leave me with this right-hand side. So what we're going to do is take 1 and subtract a binomial CDF. Your trials are still 5. I'm still looking for 5 people. My probability has not changed, but now I need to really pay attention to this X value. Looking at the left, the lowest or the highest X value that I have over here is 2. So I'm going to type this in just all at once. So I have 1 minus my binomial CDF of 5.1, and I need this to be 2. And we get 0.0086. Okay, definitely a smaller percentage there again. There's a rare chance that there was a fast runner to begin with, so it's very rare that I would have 3 of them, 4 of them, or 5. Watch out for those at least problems, or anytime you're looking for a greater than, you're always going to do 1 minus, and then your X is always 1 less than what you're looking for. Okay, part E is a little bit tricky as well. Part E says find the probability that there are 2 or 3 fast runners. So what I'm doing here is finding the chance that X is 2 or the chance that X is 3. 2 equals, so what I'm going to do is use 2 PDFs here. So I'm going to take the binomial PDF. 5 is still my n, my probability is still 0.1. I'm going to start with this first one of X equals 2. And whatever I get there, I'm going to add it to a binomial PDF for 3. So still 5 trials, same probability, but now I have 3 as my X. In your calculator, you can type these in separately and then add them. You could type them in all together. Should not make a difference in your answer. So there's my first one. Binomial PDF, cutoff of 3. So we should get 0.081. Okay, why don't you guys go ahead and take a minute to try F, G, and H. Once you're done, go ahead and play your video. I'll show you my work so you can check your answers. All right, here are my answers for those last 3. Part F was pretty, I think, self-explanatory. It was just an equal, so you're using a PDF where your X is 4. You get a very, very small percent there. G is a tricky one. It was an at least 2 fast runners. So this is similar to what we saw above. At least 2 means I'm looking for greater than or equal to 2. So once I write out my little sample space here, I'm looking for really less than 2. So I did 1 minus the binomial CDF, but using X as that cutoff because that is the first thing that's not equal to 2 and is less. Okay, part H was tricky. Make sure you check your answer here. This was looking for less than 4, so 4 should not be included, so it's just a less than 4. So again, when you think about that sample space, the highest you should go to is 3. So your X value should be a 3 there, not a 4.